Hello everyone. My name is Varun Chaudhary. I am a senior research fellow at School of Material Science and Engineering with Professor Raju Veeramanujan. Today's class will be focused on accelerated discovery of magnetic materials. These are the outlines of today's class. Why accelerate engineering innovation, how to accelerate the innovation, and identifying new magnetic materials with good property set using a range of synthesis methods like additive manufacturing, spark plasma sintering, magnetron sputtering, chemical flow synthesis, and then summary. Basically, in this lecture, we will know how can we accelerate the materials development using a range of methodologies. So the question is why to accelerate innovation? What are the challenges we have? So let's say someone wants a material of X, Y, and G properties. Then there are lots of possibilities to find a promising candidate. Like lots of elements in periodic table, one can alloy them together or little bit doping. And when we alloy or dope, the crystal structure change and the similar fashion, the final properties also change. Doesn't matter it's magnetic, mechanical, or whatever property we are looking for. So now, how to choose and which one to pick? This is a very difficult and open questions in front of researchers. So in last slide, I mentioned lots of possibility. Let's see how many possibilities could be. So let's consider a system which is made by a C components, and let's different materials be distinct if they differ by X percentage. Then the total number of materials can be defined by this number. And very conservatively, let's consider the component 60. We know that periodic table has around 120 elements, but some of them are radioactive and toxic, so we just focus on the like metallic and non-metallic elements. And C60 and the X means to differ one materials to other is 0.1%. And why I choose this 0.1%, that we have very beautiful examples around us where we can change the property by adding 0.1% of second element, like we have steel here, and in semiconductor industry also adding a little bit additional element can change the property significantly. And putting the value in this equation, so we get a huge number, 10 raised to power 100, which is one Google. And I believe that this may be that's why the Google may be Google, just a spell difference. And for comparison, there are 10 raised to power 80 atoms in the universe, and the size of universe is 10 raised to power 34 nanometers. So there are more potential materials we could make than there are atoms in the universe. So see, this is a very, very big number. 10 products by 100 times. And the old way to identifying a new material is something that out of that big number, we just pick 1 or 2 dots and then synthesize, characterize, and then property evaluation. And we repeat this process year by year. So the outcome from here is what? It's very, very low possibility to get the desired properties and discovery of new materials. So what we missed here, the new discovery and the money, energy, and of course the time. So time taken from laboratory to real application is around 30 years. So the new way of discovery can be accelerated discovery method, for which what we do, we pick a set of dots and then do the combinatorial synthesis, high throughput characterization, fast property evaluations, and then we learn from the results. This is a cyclic process, and both results are important here, whether they are negative or positive. And with this methodology can result a very good discovery. We can means high possibility to get new materials. So what we save here is time, money, energy, and of course a climate, because they all are basically linked. And time taken from laboratory to application can be cut to 3, 4 years. So using high throughput experimental techniques, high throughut computational techniques like AI, machine learning, DFT calculations, and all, and the characterization and property assessments using automated tools, one can accelerate the material discovery 10 times or even faster. And accelerated material development is not only limited to the magnetic materials, it can be applied in all field of material science, composite materials, to design IC design, battery material, polymers, catalysts, etc. This class is mainly on magnetic materials, so my lecture will be mostly focused on the magnetic materials development. So soft magnetic materials are critical to the performance of electric machines and drives. They are ev almost everywhere. They are used in transformers and in power electronic converters, e-vehicles, wind turbines, etc. And they play a vital role in green energy. For an example, around 65% of United States electrical energy is consumed by motor drive applications. And the scenario is not much different when we see the global picture. Therefore, there is an urgent need for a superior magnetic material. So here are the key challenges to use soft magnetic materials in advanced applications. So materials should have a magnetically soft, it should have a high strength and high value of electrical resistivity. Then only we can have improved performance. So the next generation electric materials need a combination of material property. They should have a high saturation magnetization, low coercivity, high permeability, high value of electrical resistivity, and high strength. Here we see the graph for saturation magnetization versus coercivity for all available soft magnetic materials. And if you see this graph, is that a material which is having low coercivity, the saturation magnetization is also low. When we want to increase the saturation magnetization, the coercivity also increase. But we need a material which has coercivity low and saturation magnetization high, somewhere in this region. But the challenge to get such material is that the coercivity and strength, they all are depend on the microstructure. They are very, very sensitive to the microstructure and processing parameters, and the length scale of microstructure, how they depend, is completely different. So therefore, when we want to increase the strength of the material, the coercivity also increase. The another challenge is when we see the magnetization versus resistivity. Usually, the material which has high saturation magnetization, like iron, cobalt, and uh, iron silicon, they have a low value of electrical resistivity. When we want to increase the resistivity, the saturation magnetization decrease. Sorry. So why we are looking for a material which is having a high resistivity? The reason behind it that the total power loss or eddy current loss is indirectly proportional to the resistivity. When we have a high value of resistivity, we can cut the eddy current loss significantly. So this is a mass engineering problem, and can be solved by machine learning or AI type of approach. However, the main problem is that for using such kind of approach, we need a database. And there is no database available where we can get magnetic, mechanical, and electrical properties for these materials. Usually, either we have a magnetic property or we have electrical property or mechanical property. But getting all property together is very, very difficult because it's two different field of research. Therefore, our focus is to develop the materials library so that we can apply machine learning and AI kind of approach to find out the global maxima or global minima for these properties. So in our group, we are using several kind of high throughput strategy like additive manufacturing, which is lens, and spark plasma sintering, co-sputtering, chemical flow synthesis. Then after preparing the material, we use the high throughput characterization method, micro XRD, micro XRF, and then property evaluation using magnetic field assisted TGA, nano indentation hardness, and we are also using the thermodynamic modeling and machine learning. So let's start with the high throughput additive manufacturing approach. So there are many techniques for additive manufacturing, like selective laser melting, binder jetting, and lens. So here we will focus on lens because this has additional advantages. Using this technique, one can prepare a material which has a systematic change in the composition from one side to another side. And that's how we need. So that in one sample, we can have a multiple composition and we can easily quickly explore the range of composition in the material. I'll let you know how it works. So this is the schematic here. And we have hoppers, powder hoppers. It depends on the machine. Some machines have two and some four. So, and by changing the feeding ratio of these powder, one can change the composition from bottom to top. The laser is coming from this, and you see here, it print line by line and layer by layer. And by changing the flow from hopper 1 to hopper 2, one can change the composition. So see the powder is coming from the nozzle and laser is at center, and the laser melt the powder and the composition will be whatever is coming from here. So see we can prepare using this technique either a discrete change in the composition or it's a gradual change from bottom to top. I mean, very recently we have prepared a prototype which had change in composition from center to circumferences. So it's a rapid testing of composition space and the ability to manufacture bulk materials with systematic composition variation offer a great potential and significant advantages for the over the conventional processing method. These are the results on iron, cobalt, nickel ternary alloy system. We have explored the complete space of this and the composition change from bottom to with the 2 mm interval. And this is here we have a phase map. This we have constructed using automated X-ray diffraction techniques. So here in one sample we have several compositions. And the crystal structure for this change from pure FCC to BCC plus FCC and then pure BCC. And some region we identify where we have a third phase, like HCP, and here we pure phase. And not only this phase map, we can also quickly see what's the grain size and how the grain size change with changing the composition. And it's not just a little bit change. You can see here the grain size change is starting from 1 micron to 40, more than 50 micron. So there are some regions where we have a very big grain size. And yes, these grain size and phases, we know that directly influence the final properties. This is the magnetic and electrical properties of these iron, cobalt, nickel ternary alloy system. And the saturation magnetization, we see that there is a gradual change in the saturation magnetization. However, in the case of coercivity, there is no trend at all. This is one region where we have a higher coercivity, but in other region, it's not a proper trend. In case of electrical resistivity, we identify few regions where we have a high value of electrical resistivity. So By having such maps on our tables, one can easily identify the regions of interest, region of optimum set of properties. For example, this is something. This if you see this region, we have a kind of moderate high saturation magnetization and low value of cohesivity and very high resistivity. So such materials can be very useful for next generation electric vehicles and all. This is just expand of one sample which is having a 7-8 composition, and you see by changing the phase from FCC to BCC, the Wicker hardness change a lot. It was close to 100 and then reached to 400. So see, this kind of material can only identify using such accelerated development techniques. Otherwise, one could have missed this. So there is a large variation in hardness in one sample, is starting from 90 to more than 400 Wicker hardness. So here we plotted the radar plot, which is basically from complete space. We first pick the composition based on the best property. For example, the composition with best saturation magnetization, the composition with best coercivity, resistivity, and all. And we also use the cost of the material. For this, one can easily find out the material what they need. For one particular application, they may be very interested for the saturation magnetization, but less interested in other properties. For some application, cost is important, but for others, it may not be that important, like in defense application. So high throughput spark plasma sintering approach. Next, we will discuss on high throughput spark plasma sintering. So this is another technique we have we are using in our group, that in one sample we can have multiple composition. And what we do here, we first prepare the alloy powder. Whether we can prepare it using ball milling or chemical method or whatever, and then we fill those materials into the die set, and then press at high temperature using spark plasma sintering technique. So we have several libraries on that, but I'll discuss mainly on iron, cobalt, nickel. So for that, we have prepared multiple pellets with the range of composition from bottom to top. And here you see the contrast difference when we cut it and polish it from one composition to another compositions. And we could, the main advantage of such techniques is that the characterization and property evaluation is very quick. We can save lots of time for that. For example, when we see the phase, you want to know the phase, whether any change in the phase or not. So one sample we just put here, apply the X-ray, and the X-ray can be automatically scan the sample through one side to another side. This is completely automated way. And then we can get to know what's the crystal structure, what's the lattice parameter for the particular composition. Using this practice, we have completed this space and found that this region is face-centered cubic structure. Here we have body-centered cubic structure, dominated phase, and somewhere in between is BCC plus FCC. So it's a rapid characterization to identify the phase and lattice parameters of the material. Here we have saturation magnetization versus coercivity, Curie temperature, hardness, and resistivity. So you can see the significant change along the sample length in every property, saturation magnetization changing, Curie temperature changing, hardness, and resistivity. And for Curie temperature, we are basically using a very fast technique, We just apply a small magnet near to the TGA pen, and this small magnet attract the sample, and at the Curie temperature, lose the attraction with the sample. Therefore, we get a transition, and this we have checked with the conventional technique, and it's exactly matched. And just to repeat what we are looking for, the saturation magnetization should be high, coercivity should be low, and the Curie temperature higher is the better. Hardness should be in higher side, and resistivity should also be high. These are the property map. And yes, actually there is no single composition. If someone say, I want the max, the best saturation magnetization and the minimum coercivity, oh no, it's not possible at all. But yes, one can easily identify the compositions which has optimum set of properties. See here, I have this all. So this particular region, we have saturation magnetization close to 150. Curie temperature is also around 800 degrees centigrade. Coercivity is two-stirred, and then the same good value of resistivity. Here we have all the properties like variation in saturation magnetization, resistivity, Curie temperature, coercivity, and weaker hardness, and the cost. So if someone want a material which is having a low value of coercivity, just pick this composition and this and go to here. They will get to know what's the composition. If one is interested to very cost effective material, this is something here. In the same way we can find out. This is again a spider chart for selected composition. Yes. So we have validated our methodology using conventional method. So we have selected selected samples which which given us the best properties, like these are the composition, and we prepared these composition using conventional method and compared with the one which we have observed using high throughput one. So the red curve here is the property for the sample prepared by high throughput methodology, while the black one is for the conventional one, and the blue one is the difference between these two. You see, there is an excellent agreement of the trend in all the properties like saturation magnetization, coercivity, Curie temperature, Wicker hardness, and the resistivity. And not only that, the absolute value is also very, very close. The saturation magnetization earlier it was 202, close 202, and now it's 203. The Curie temperature. However, the properties like coercivity, there is a change. Earlier it was 2.1 and now we have 7. And this is because the coercivity is very, very sensitive to the microstructural defects like porosity and all, and therefore we are getting some difference here. But the main advantage of this that we can get a trend. And if we get a trend that the particular composition which is giving us a good value, we can post process and can get improved performance. Therefore, our methodology has been validated with the conventional one, and it's so a very good trend match. Next is high throughput chemical approach. So yeah, so this is the setup here built in our group. So what we have here, this is the device which is having a zigzag channel design inside. This is the pump, and these are the precursors and reducing agent, and then NaOH to maintain the pH and all. So we have 3 inlet and 7 outlet here. So by changing the flow rate of these precursors, one can change the composition of the outlet. So this is the advantage of this. And the additional advantage, at one flow rate, we can get 7 composition. For another flow rate, set of flow rate, we can get another 7 composition. So it's a very, very fast technique, and can quickly synthesize so many samples. And yes, here is the you see the difference in the properties and the phases. The material which is coming from the channel 1 is showing face-centered cubic structure. C4, it's a body-centered cubic structure, and it's changed to BCC plus FCC or FCC plus HCP. And not only phases. If phase change, the other thing automatically change. Like see the difference in the morphology, and you will see the difference in the properties as well. So same, we have applied the spark plasma sintering. We have used the spark plasma sintering to make the powder into bulk form. And for that case, we have designed another die set. We are not limited just to 5, 6, 7 sample in one run. We have designed another die which has a multiple cavity channels, whatever name we can give. And then in one cavity, we can have multiple samples so that the total number of sample composition can be prepared like 30, 40 composition in one run, just 1 or 2 hours. And then we can do the fast characterization of these graded samples. These are the next is compositionally graded iron cobalt nickel film using. So this is a little bit different than what I have discussed so far. What we discussed is bulk material, additive manufacturing, spark plasma sintering, and chemical flow synthesis. Earlier it was powder, and then we converted it into the bulk using spark plasma sintering. Now this is a thin film technique, but it's a very, very efficient technique. One can easily have a lots of composition doing the coach sputtering. So like for this, we have two targets like cobalt and permalloy, nickel, iron, and then sputter together. And you see the change in composition from one side to another side within across the sample. Then one can have a different library using the either we can have a heating temperature, substrate temperature different, or post processing condition different. So in our case, we have chosen 5 different libraries. Like first we prepare the film at room temperature, and then substrate temperature was changed to 300, 500, and the another condition is that room temperature film was annealed at different temperature. And then property evaluation characterization. In the same way, all properties were plotted together. We've identified that this particular library, which was ML500, given the best properties, and you see the change in property. In all the properties, there is a significant change. The coercivity changing from cobalt side to nickel side. The resistivity is higher in somewhere in the between. Yes. So as a summary, our high throughput methodologies like additive manufacturing, spark plasma sintering, chemical flow synthesis, or coach sputtering, and the characterization tools, what we are using, XRD, XRF, EBSD, and property evaluation tools, resulted at least 10x acceleration in the magnetic materials discovery, and which is highly, highly required. We are also using the machine learning and computational thermodynamic calculations, what I have not covered in this lecture. So there are lots of scope to find the new materials with desired properties, and accelerating engineering innovation must be the new normal now that we have learned from here. So let me acknowledge lead PI, Professor Raju Ramanujan, our team, and our collaborators, funding agencies. Thank you very much. Thanks a lot.